So the next section is on augmented matrices. Now this section I think is a lot easier than the previous section we just looked at, because really what it does is it takes the ideas from the previous section and well, it cleans up the methodology big time. Ultimately, an augmented matrix, the goal of this section, by the end of this section, you will be able to solve linear equations, not having to use graphing, not having to use substitution or elimination, but instead using the calculator, which is very convenient. But we need to work up to that. We need to understand some terminology and stuff, and then talk about how to put it in the calculator, which I do have in the notes if you end up forgetting. So let's start off with not an augmented matrix, but just a matrix. A matrix is just a rectangular array of numbers. It's basically, and you can look in example 1 down here, some examples of matrices. They have these brackets on either side. That's the general notation. And within the brackets are these numbers listed in a grid-like pattern, in a table-like fashion, if you would. And so these numbers do not add or subtract each other. They are just listed there. Their order does matter. You have to put these numbers in a specific order. If you switch up any of the two numbers, you will completely change your matrix. The order matters, but it's just a list of numbers. Now, you will hear me refer to the matrix by some special characteristics, such as rows. Now, any row, as you would imagine, runs horizontally, and the columns run vertically. So for the second example down here, this would be a row, and this would be a row. Or this would be a column, that would be a column, that would be a column. Something that's important that we'll use throughout this section is the size of a matrix, which is notated as rows by columns. So rows, so you figure out the number of rows, you put an X, and then you figure out the number of columns. And so we're going to be using that, and we'll talk about how to find that in example 1 here. A square matrix is a special type of matrix. Well, it has the same number of rows and columns. So a square matrix has the same number of rows as it does columns. A row matrix has only one row. A column matrix has only one column. So these are some terms that we throw around. And as we go through this section, hopefully this will become a little bit more intuitive. But let's talk about the notion of establishing this terminology and figuring out these characteristics of a given matrix. So for example 1, for each one of these matrices, we're going to figure out the size. We're also going to figure out if the matrix is a square matrix, a column matrix, a row matrix, or doesn't really have a special type to it. Let's start off with the size. Now the size of a matrix, we need to figure out the number of rows, which you look at. There's no computation to it. There's one row here, there's one row here, 2 rows in total. So I'm going to put a 2 right here. So that refers to the number of rows. The notation tells us we put an X, which means by. So it's a 2 by something. And that's characterized by the number of columns. Here's a column. Here's a column. There's 2 columns in total. So 2. So we would say that the size of this matrix is a 2 by 2 matrix, because there's 2 rows and 2 columns. That's it. That's how you find the size. Now we want to characterize this as a square matrix, row matrix, column matrix, or none of the above. Now, this one's going to be a square matrix. This is a square matrix because the rows equal the columns. The number of rows equals the number of columns. They're both 2. And that's it. That's all we have to do for this problem. So if this stuff seems easy so far, then the first half of this homework is going to be pretty easy. Let's move on to the second one. Let's figure out the size of this matrix. Well, it seems like there's 1, 2 rows. Yeah, and you have the right idea. There's 3 columns. 1, 2, 3. 3 columns. So it's a 2 by 3 matrix. That's what we would refer to it as. So if I say the size of a matrix is 2 by 3, then you would think, all right, it's got 2 rows and 3 columns. And so we also want to consider, is this a special type of matrix? Is it a square matrix? No. Not a square matrix because the number of rows is not equal to the number of columns. So it's not a square one. Is it a row matrix? A row matrix, we're only allowed to have 1 row. We definitely have more than 1 row. Same thing with the column matrix. Yeah, so this one doesn't really have a special type. So this one's no special type, really. Because a column matrix would only have 1 column, and we have 3 columns. So it's not really a special type to it. So yeah, what would the size for the third one be? It'd be 1 by 4, that's right. 1 by 4. It's a little trickier. It's triviality contributes to its own, perhaps misleading speculation. There's 1 row here, so this is a single row, and it does have columns, even if the columns only contain 1 number, but those are all columns. So it's a 1 by 4. So this one we'll characterize as a row matrix, because there's only 1 row. So that's how you figure out the size and the type. Mainly, we're going to be using the size throughout this section. Types, not so much. Does anyone have any questions before we move on? So again, if this stuff seems pretty straightforward, the first couple of problems on this homework you should be able to knock out very easily. So far we've been talking about the matrix as a whole, but what about the individual numbers in the matrix? Well, we refer to those as elements. An element is just any number in the matrix. It's the numbers inside a matrix. That's an element. You can reference an element by using this notation. It's a lowercase a, and it has a subscript, which means it's a little label next to the A, and it gives you 2 numbers. The first number tells you what row, and the second number tells you which column. So you might be able to see in example 2, that little notation right there that I just circled, the lowercase a, and it has a little 2, it looks like a little 23 next to it. The 23 is actually read as 2 and 3. The 2 represents which row, and the 3 represents which column. And we'll talk about that here in example 2 in a bit. There's also the principal diagonal. Now, there's a bunch of diagonals out there. We can look at diagonals slanted this way, this way. A principal diagonal starts from the top left corner and moves diagonally down the matrix. And so it's really more so a list. It's not just a number. It's not a distinct number. It's really a list of numbers. So let's talk about how to find all of those with these two examples. This should be pretty straightforward as well. Yes?
Would you count down for the row and over the column?
Would you count down for what?
The row and over the column?
I mean, ultimately, let's just look at an example, and you can ask me afterwards. So let's go ahead and look at example 2, part 1 here. And so just to give you, just to construct this based off of previous stuff, this is a 3x3 matrix, and it's a square matrix. Again, not really needed for the problem, but just as a metric of review. This notation over here says, I want to know the element that is in the, so remember, that's not 23, it's 2 and 3. The first number tells you the row. I want to know the element in the second row and the third column. That's what this is asking for. Second row, third column. So the second row is this one right here. Third column is this one right here. That's the 7. So it just wants the 7. That's the answer. It's just 7. Let's look at the next one. Here it wants the, well, it's not 11, it's 1 and 1. The first one is always for the row, and the second one is for the column. Well, the first row is the top row. First column is the leftmost column. We want the -1 here. That's in the first row in the first column, the -1 up there. Let's do one more. The 3, it's not 32, it's 3 and 2. Third row and the second column, what did you say it was? Let's see, third row, second column, it's going to be the 4 here. Third row is the bottom row, second column is the middle column, and it's 4. So notice it's just asking for a specific element in the matrix based off of telling you the row and the column it should be in. The principal diagonal, you always start from the top left, whatever the top left number, which is -1 here, and you work your way diagonally down. So you can think about it as you go down 1 across 1 to 8, go down 1 across 1 to 0, and we're out of numbers. So that would be 8 and 0. It's a list. It's just every number that's in the diagonal. The principal diagonal, principal just says, we're going to look at this specific diagonal. So let's look at problem 2 for a little bit more practice. So again, they're asking for the second row and the third column for the first one here. The second row and the third column is 5. First row and the first column for the next one is the 2. What about the next one? The answer does not exist. This one, it does not exist. Because it's asking for the third row in the second column, but we don't have a third row. We only have 2 rows. It wants the third row, which doesn't make any sense. So this notation doesn't make any sense for our problem here. Did for the previous one because we had a third row. This one we simply don't. And the principal diagonal, you always start at the top left. So we can start off with the 2 here. and you could think about it as going down 1, across 1. Okay, there's the 1. We can't go down anymore, so we're actually done. That's it. It just kind of ends abruptly, which happens. So does anyone have any questions about this before we look at augmented matrices? So from here, we can go ahead and look at augmented matrices. And when I add the word augmented, this means that this is in relation to something. So we were just looking at matrices alone, which we talked about what they look like, some notations and characteristics of them. An augmented matrix now will associate with a system of linear equations. So this is going to tell us how matrices actually help us solve systems of linear equations. So it is a matrix that is created to solve a system of linear equations. And how do you solve a system of linear equations? Or what does that mean? It's the point of intersection between two lines, or in general, 2 or more lines. So we need to figure out a way of taking a system of linear equations, like 1 and 2 here, and writing them as a matrix. We're just going to start off with that step first. So we're going to build up to this. So here's a giant system of linear equations. We would not want to do graphing solved by this or that. We would not want to do that for this problem. It would take forever, and the algebras would be outrageous. So instead, we would want to find something called the coefficient matrix. We don't really use it too much. It comes up in, I think, 1 or 2 homework problems, and so I wanted to make sure you all know about it. So we'll start off with this thing called a coefficient matrix. And so since it is a matrix, it has that bracket notation, which I'll go ahead and put here to start it off. Now, what does the word coefficient mean? Well, the prefix co means with. And so coefficient, it's referring to the numbers that are with variables. So any number that's with a variable, that's a coefficient. So what we want to do here is we want to take all of these numbers from our system, basically get rid of all the variables, all the addition and subtraction, keep all of them in the same order, and translate that to a matrix. So what I mean by that, let's just look at the first column here. The coefficients, I think we can all see, are 3, -4, and 7. So guess what the first column of our matrix is? 3, 4, and 7. And they have to stay in that order. You have to keep the ordering. You switch them up, the problem's going to be wrong instantly. So what about the next column? Yeah, so notice it's 2, 11, and -8. We're not adding or subtracting numbers. We're simply listing them from the system. We're listing them. And then, you might see the pattern by now. So we have -4, -10, and 1. Yes, and 1. There's an understood 1 right here. Whenever there's just a variable by itself, there's an understood 1 in front. And so since we only are looking at coefficients, which means numbers with variables, that's it. We close it off. Because the 18, the 13, and the -4, there's no variables next to them. So we don't include them. So that's the coefficient matrix. We just take every number and we translate it in order to a matrix. Now, the coefficient matrix is not going to be as helpful as the augmented matrix. The good news is, though, we pretty much have the augmented matrix. The augmented matrix is actually constructed from the coefficient matrix. So all the numbers we just found carry right over. So that's the good news. The augmented part says, all right, give me the last column as well. I don't care that they don't have variables next to them. So the last column, of course, is the 18, 13, negative 4. So we're going to add in the last column, 18, 13, and a negative 4. And now we close it off. So the augmented part says, just give me everything. I don't care if it has a variable next to it or not. Now there's one stylistic thing that we have to do here that you'll probably notice in your homework. You might even notice it at the bottom of the screen here. A part of the notation is that we normally add a vertical line separating the last column from all the other ones. What this vertical line does is it gives the reader an understanding of where the equal sign would be. So, or in other words, it splits up the coefficients from the constants. Because notice everything on the left is the coefficients, and everything, and the stuff on the right are the constants. So you will see that vertical line, and I just want to emphasize what it's there for. Really, it's more of a stylistic thing. If you don't put it, it's not really going to change much of anything, in all honesty, but that's why it's there, though. Let's do the same thing for problem 2, and I'll ask if anyone has any questions about this so far. So, with problem 2, let's go ahead and find the coefficient matrix. Which, this one's going to be a lot smaller because we have less equations, less variables. So let's start off with the first column. There is a negative 4 and then a blank. What do we do there? That's right, it's 0. It's a 0. It's understood to be 0 times whatever the variable is. It's 0. So if you ever see a gap, then you know to put a 0 in for that spot in the matrix. And then I think the rest of them are pretty clear. Yeah, there's a 4 and a negative 2. And then there's a vertical line because that's all. Wait, so this is the coefficient matrix. That would actually close off right there. That would be the coefficients. Then the augmented would basically just add that last column. So again, negative 4, 0, 4, negative 2, vertical line, and now we add that last column of 2 and 9. 2 and 9. And again, the vertical line represents where the equal sign will go, or additionally, it's separating the coefficients from the constants. Does anyone have any questions about this before we proceed? Again, we haven't really done anything computationally at all. So that's, of course, always good news. That means a lot of problems you can knock out fairly quickly by doing really minimal work. So example 4, we're going to work backwards now. Can we build the system given the matrix? And they say use the variables x, y, and z. We might have to use z, we might not have to, but it says use those however many you need. So notice they give us the matrices, we have to build the system. So really what we need to think about here is where do the variables go? And really each column represents a different variable type. But it's not x, y, and z. The last column is not a variable type. That's what the line helps us distinguish. So here it says 8x and 5x for that first column. Now we need to add arithmetic to this, so plus 4y and minus 2y for the second column. And then the vertical line tells us that we have equal to 3 and 7. So that's pretty much this process that we use here. Again, it's not x, y, and z because the 3 and the 7 are constants. You have a question?
So is it only z is the third column?
Yes, so z would represent the third column that isn't marked off by a divider. So you might kind of foreshadow the next problem. We're going to be using z there. So for this next problem, yeah, you would have an x for the first column, a y for the second column, and a z for the third column, because that is still part of the coefficient part of the matrix. The last column, they're not coefficients, so they don't get a variable. So now we can put 4x, negative 11x, and technically 0x. We'll talk about that here in a second. What's that? So the next column, it would technically be plus 0y, plus 17y, and plus 4y. Notice I'm throwing in addition signs because now ideas of arithmetic are coming back. And then plus 3z, plus 0z, and plus another 0z. Again, they tell us to use z if we have to, and here we definitely need to. And the vertical line tells us that we have equal to signs to whatever the corresponding numbers are. Now, I'm not too sure how picky my math lab is about simplifying. I'm not too sure if it'll accept this with the zeros, but to fully simplify this, you could take out all the zeros. And that would be considered simplified. Again, I don't know which one it accepts, so I'm just going to give you both of them, and you can try whichever one you like and see in whichever way they make you format it. Because I've seen stuff both ways, so I'll just give you both. Okay, so that's how you convert from a matrix to a system. Does anyone have any questions before we now see how to put this in the calculator? Okay, so this does imply that you should probably pull out your calculator now. If you would, I do recommend you should follow along with me. Make sure you can do it at least once. And of course, the way you do it in your calculator is, it's in the notes here, literally button by button. So if you forget about how to do it, it's here step by step. You better utilize it because it takes me forever to type these up. So, but that should tell you exactly what to do. So let's say we're given a system, such as in example 5. So you think to yourself, all right, I'm tired of doing this by hand. Can I just do it? Can I just give this to the calculator? You sure can. Got to give it to the calculator in the right way, though. So you would take that matrix or that system and write it as a matrix, just like this. So I already went ahead and put the augmented matrix. Notice it has the vertical line and everything. So make sure you see why that matrix is as it is. And so once you convert to a matrix, then we get to, now that we have the matrix form, we could feed the matrix form into the calculator directly. And we're going to use a command in the calculator called, it's called the row reduced echelon form, or RREF, RREF, stuff like that. So let's talk about how to do that exactly. There's really 3 steps to this ultimately. But the main thing you need to realize is how to get to the matrix menu in the calculator. Let's have a fresh calculator screen here. So the matrix menu is found by pressing second And then if you go down 1, 2, 3 buttons, well, the button here says x to the negative 1, but right above it, you should see the word matrix. And as soon as you click second and x to the negative 1, so that would be the first step in this calculator tutorial here. Then, what's that? So, so that would bring you to the matrix menu. So what we're going to do in every incarnation of this, you will always go to edit first and then math, then names, just as a general overview. You move your cursor to the left and right, you see different things. Names and edit look pretty much exact for now. Edit is going to be where we edit the matrix into the calculator. So that will be the first thing you always do. You go to edit. And to make things easy, we're always going to edit matrix A. So I'm going to press enter. So make sure your cursor goes over to edit and press enter. Make sure your cursor is on A, as it should be by default. Press enter. Once you do that, you should have this menu here, and it's asking for, all right, give us the matrix. We want to know what the matrix is. But notice it only gives you one, there's only 1 0 down here. We have 6 values we have to type in. So you should notice my cursor is blinking near 1 by 1. We don't have a 1 by 1 matrix. In fact, as you see on the top of the screen, the size of the matrix is a 2 by 3. There's 2 rows, 3 columns. So guess what we have to do here? I'm going to type in a 2, enter, 3, enter. And notice, as I type those in, the matrix grows, expands to where it will allow us to type in the 6 values in the right positions as well. So just like similarly to how we did with the stats programming, we type in each number and press enter. It'll shift you to the right, so make sure all the numbers are aligned consistently with the way that they are in the notes here. And if you need the numbers, they're also here as I follow along this diagram. So again, you want to make sure the numbers are aligned properly in the calculator. And so once you have this edited into the calculator, so now the calculator knows, all right, this is the matrix you want us to do stuff with. Just like we did with the stats section, you're going to press second and mode to go back to the main screen. We're going to go back to the matrix menu a second time, because now we need to find the command that makes all of this magical stuff happen. This command can be found under math. You scroll down a bunch, and you will see RREF. That's the command we will use. Don't use just ref. That one's not as powerful. We want to use RREF. That one will do everything for you just very quickly. So you want to press enter on RREF, so RREF. But now it's got an open parenthesis, which implies, all right, you need to tell me, all right, I'm just a command. You need to tell me what I need to solve. What thing am I working with? So we have to go back to the matrix menu one last time. Now under names, you will see 2 by 3 next to A, and that is our matrix. So under names, so not under edit, but under names, let's press enter on A, and it'll say, all right, RREF, I want you to work on A. Let's close the parenthesis and press enter. And if you did everything correctly, you should get what kind of looks indecipherable. Yeah, it doesn't look legible at first, or you may not understand what this means at first. But you should get what I have on the screen here. If you have a fancier calculator, I think it'll look a lot fancier on your screen, but all you care about with this is the last column. That's all you care about every time, the last column. And in order, what that tells you is what your X value is and what your Y value is. So it tells you that in order. You have a question?
Mine's not bracketed like separately, it's one bracket.
You must have the fancier one then.
Oh.
Did you get -3 and -2? Okay, then it doesn't matter if it's broken up or not. Yours is just fancier. So what this gave us is the point of intersection, which is the solution. So no more need to do the elimination method, substitution, graphing. Calculator does it for you. So that concludes that problem, actually. That's what you have to do. So this is a process you need to familiarize yourself with, especially come the final exam time. That's mainly it. And we're going to do a few examples just to emphasize this idea. But does anyone have any questions before we practice this process? If not, I'm going to scroll down to example 6 here. And we're going to solve this system, well, this system in the next one, using augmented matrix methods. So the first thing we need to do with any system is write it as a matrix. And so I'm going to breeze through this one kind of quickly. Hopefully you all see where these numbers are being derived from. So hopefully I didn't lose anybody there. Because from here, what I mainly want to focus on is how to put this into the calculator. And so I'll go ahead and write out what that next thing is going to look like. So I'd like to have a fresh screen here. I'll clear that out. So what I'm going to do is go to the matrix menu, second and x to the -1. Go over to edit, because I need to edit the matrix in. I need to make sure the size is correct, which it is. We have a 2x3 matrix here. So it's a 2x3 matrix. So we have enough spaces. So 2 and 3 are fine. I just typed in 2 and 3 again. It doesn't matter. And I'm just going to type over these numbers that are here from the last problem. So I'll just put 3, -1, 5, 15, 2, and 4. And so once you type all of those in, you quit out the menu, or yeah, you quit out to the main menu, so second in mode. Now, if you're good with the calculator, you could press second and enter to pull the previous result from your calculator. So that's second and enter. Or you can go and derive them one at a time. Go to the matrix menu, to math, find RREF. Second, and the matrix menu one last time to pull an A, because that's what you want to work on. Close that up, and you get, well, that's weird. You should get that, by the way. We are going to fix that here. So what we actually get is a bunch of 6s and a -3. Well, one of these values came out nicely. The other one, not so much. And knowing my math lab, it's probably going to say, I want a simplified fraction. Now you might already notice that that's 2/3. What about if you don't? So you have to do one more thing. So if you had a number that was a decimal and you wanted to convert it to a fraction, do you know what to do to convert a decimal to a fraction in the calculator? Well, if you do, then you also know how to simplify this. Click on math. And yes, so you have the right idea. So you click on the math button, which I'll just put right here. And then you're going to click on convert to a fraction. And guess what? It also works for matrices, which is very convenient. So you press enter. Notice it already puts A and S, which means the matrix, convert that to a fraction. And guess what? It cleans it up for us big time, which is a lifesaver.
So it's understood to have that augmented line.
Yeah, I write it as habit because I've been doing this a long time, but it's always understood that that line's there, always separating the last column from the other ones. So it's always separating the last column from the other ones. If I don't write the line, then it should probably be there anyways. That's for augmented matrices. If it's just a matrix, remember, a matrix by itself doesn't associate with anything. Augmented matrices are associated with something. But in any case, last column tells us everything we need to know. And it tells us in order. It tells us that x is 2 over 3. It tells us that y is -3. So ultimately, the point of intersection is 2 over 3, comma, -3. So that's how you use the calculator to solve systems. Does anyone have any questions about that before we look at the Goliath next example? So if not, let's go ahead and look at part 2 down here. So this one, you would definitely not want to use substitution, elimination via addition. There's way too many variables, way too many equations. It would take forever. So instead, we'll just tell the calculator to do it, which means we need an augmented matrix first and foremost. Again, I'm going to breeze through the numbers here. Hopefully you can convince yourself of these numbers belonging where they are. And we're going to need the size of the matrix, which looks like a 3 by 4. We have a 3 by 4 matrix. So let's pull up the calculator. Start with a fresh screen. Go to the matrix menu and go over to edit so I can edit this matrix in. We don't have a 2 by 3 matrix anymore. We have a 3 by 4. So I'm going to type in 3 by 4. And you might notice, I don't know if this is true for just this calculator or all of them, it only shows 3 columns. It's because the calculator is, it can only show 3 at a time, but if you scroll over, it'll show you the 4th one. So it can only show you 3 at a time, but if you move your cursor around, you'll see that there's actually 4 columns. And from there, we can type in the values. -4, there's 18, -4, 11, -10, 13, 0, 7, 1, and -4. So again, it only shows 3 columns at a time, but there are, in fact, 4 there. You would just have to move your cursor around to see everything. But once you do that, now you've programmed the calculator with the matrix. We can go ahead and quit out of that. Now, if you try to do the second and enter thing, you'll probably get the answer as fraction. So you have to press second and enter again. You want to pull up this. So that's the quick way of doing it. But that's if you're better with the calculator. So you could do that, or I'll just do it the bit by bit way. We go to math, we find RREF, we go back to the matrix menu, and now we give it the matrix name. However, whichever way you do it, you will get this very messy answer, which we'll talk about here in a bit. Actually, you might already see how to fix this up, because this is just like the last problem. So it's 2.6, I don't care. It's -0.2, whatever, and -2.5, yada, yada. Again, the decimals don't help us. We need fractions. So what that implies is exactly what we did before. Second, and actually, no, not second, just math and fraction. We'll convert to a fraction. And it might be kind of cut off. I don't know if that's for every calculator. So you might have to move your cursor over to the right a little bit to see everything, because I think it cuts off a 3 for the last one. So this is actually 324 over 121, -73 over 363, and negative 941 divided by 363. So what this tells us is, remember, the last column tells us everything. It tells us that x is 324 over 121, y is negative 73 over 363, and z is negative 941 divided by 363. And that is our answer. Because there is a z in this problem as well. There's a third variable. But it doesn't really change our process much at all. Does anyone have any questions before we quickly go ahead and knock out these last two application problems? If not, we're going to go ahead and do exactly that. Very similar to the previous section, we're going to construct the system of linear equations, but then instead of having to solve it by hand, we feed it to the calculator. So when I look at system problems, I always want to look at the question, what it's asking for, so I can get an idea of what our variables represent. So we need an x and a y. How many hours does she work at each job? So there's two jobs. The two jobs being everyone's favorite, Chick-fil-A and snowball stand. I don't like snowballs, so whatever. So x can be hours at Chick-fil-A, and y is hours at the snowball stand. And that's indicative of the question, how many hours at each job? So one job, or hours at one job, hours at another job. That's our two variables. Now we need to put this together as a system. So as I mentioned in the last section, it's going to be something x plus something y is equal to some number. X plus something y is equal to some number. That's normally the template. Now, they say that she works 54 hours per week. Well, she works X hours at Chick-fil-A, Y hours at the snowball stand. Then the sum of those 2 hours is going to be 54. So the first equation represents the number of hours worked. Now it goes on to say she makes $8 an hour at Chick-fil-A. So $8 corresponds to X. $6 at the snowball stand. Snowball stand represents Y. And then the total amount of money she makes is $410. So we have our system, which means we can quickly set up our matrix, our augmented matrix. So, for the sake of time, let's go ahead and quickly throw this into the calculator. So, under matrix, I want to edit it. Size of this matrix is a 2 by 3. There's 2 rows and 3 columns, so I want to make sure this says 2 by 3. Go ahead and put the numbers in right fast like we did before. Quit out and go ahead and use the RREF command on that matrix. Pretty much the same exact process we did before. It's just a different matrix. 1, 1, 0, 0, 43, and 11. It's the last column that tells us everything we need to know. In order. It tells us that X is 43, which means she worked 43 hours at Chick-fil-A, and that Y is 11. In other words, she worked 11 hours at the snowball stand. And so that's it. That's how the calculator helps us solve this. Does anyone have any questions before we look at the last problem? Which hopefully the last problem looks pretty familiar. This one was one of the last problems. This is the last problem we did the last class period, and it's going to be the last problem we do in today's class period. So because we did this one before, so again, this was the last problem we did for the last class period, so I'm going to not focus as much on constructing the system, because X is still the base and Y is still the surcharge. This is what I said last time. So again, X plus something Y is equal to number, X plus something Y is equal to number. A customer is billed $22.15 for a 4-pound package. The first pound goes into the base price and the remaining 3 pounds goes into the surcharge. This is what we talked about before. And then that bill came out to be $22.15. A 29-pound package was $60.90. First pound goes into the base. The additional 28 pounds go into the surcharge. And we have our system like we had before. The only difference is instead of having to use the elimination method, we get to use the calculator. What are the numbers that come out of this? Let's figure that out. One, 3, 22.15, 128. If we figure this out, this tells us 17.5 and 1.55. So the base price is $17.50. The surcharge is $1.55. So that